That ugly rock you're looking at right now on your screen was valued at over $100,000. It was used as a doorstop for more than 80 years on a farm in Edmore, Michigan. But how can a rock that ugly be worth that much? Well, most people who ever saw it didn't give it a second thought. They assumed it was just a random rock. But it's not a common rock at all. It passed through generations of owners, completely ignored for 8 decades, until Professor Mona Serbescu from Central Michigan University picked it up and couldn't hide the expression on her face.
For the first time, a real meteorite came to my door. I felt a tremendous enthusiasm. This is it. I am holding this spatial rock, space rock that tells us so much about the origins of the universe at its earliest history.
The $100,000 doorstop was actually a meteorite, a 10-kilogram block of iron and nickel formed before the Earth itself existed that fell from the sky sometime in the 1930s and was forgotten for more than 80 years. And this isn't an isolated case. On the other side of the world, in Australia, a prospector named David Hull found a reddish, absurdly heavy rock in a park near Melbourne. Convinced there was a gold nugget inside it, he tried to crack it open with a saw. Nothing. An angle grinder? Nothing. A drill, acid, and even a sledgehammer. The rock didn't give. For years, it just sat there, a heavy, frustrating mystery, until he brought it to the Melbourne Museum and found out he had been trying to break open a 4.6 billion-year-old meteorite, rarer than any gold ever pulled from that soil. 2 real cases, 2 different countries, decades of waiting, and the same lesson. What looks like a common rock can be one of the rarest things that exist in the world. And the most unsettling part is that in both cases, the rock was right there, visible, within reach, and nobody recognized it. That's exactly why this video exists, and why it matters. Not to make you believe you're going to find a meteorite in your backyard tomorrow. That would be wishful thinking. But to give you the knowledge those people were missing, so that if you ever come across something strange, too heavy, too different, you know exactly what to do before throwing it away or selling it for a fraction of its real value. We're going to talk about the types that exist and which ones can be worth the most, the difference between a meteorite and an earth rock, the simple at-home tests you can run before any lab analysis, and a realistic look at how much a meteorite can actually be worth, and why not every extraterrestrial fragment guarantees a fortune. Now, to start off on the right foot, the first thing you need to know is this, and it's something most people never stop to think about, even after hearing the word meteorite dozens of times in their lives. A meteorite is not just a rock from space. It's a physical sample of the early solar system, when our planet was still forming, roughly 4.6 billion years ago. The region around the young sun was filled with dust, gas, and colliding rocky bodies. Most of those bodies never became planets. They broke apart, drifted, collided again, and some of their fragments eventually wandered into Earth's path. When they survive the fall through the atmosphere and land on the surface, those fragments become what we call meteorites, and they carry inside them a chemical and mineral record of conditions that existed before Earth's continents, before the oceans, before any form of life had ever appeared. Now, the reason meteorites are so easy to miss is also rooted in what they are. Most of them are stony. They look like rocks, because they are rocks, just rocks that came from somewhere else. A freshly fallen meteorite may have a thin, dark coating on the outside, called a fusion crust, formed when the surface melted during atmospheric entry. But that crust weathers quickly. After a few years on the ground, it fades, and what remains is something that, to an untrained eye, just looks like a somewhat dark, somewhat dense, somewhat unremarkable stone. The kind of thing people step over every day without a second thought. The Michigan Doorstop sat on that farm for over 80 years. David Hull in Australia carried his meteorite home and spent years trying to break it open. In both cases, the rock had clear physical signs that something was different. It was unusually dense, unusually hard, with a surface texture that didn't quite match the local geology. But without the knowledge of what to look for, those signs meant nothing. And that's the real problem. It's not that meteorites are invisible. It's that most people don't know what they're seeing when one is right in front of them. That gap between what the rock is and what people think it is, that's exactly where we want to work in this video. And by the end of it, that gap is going to be a lot smaller for you. Not all meteorites are equal. The scientific community organizes them into three main groups, and understanding what separates them is essential if you want to make sense of the enormous price differences you'll see when you start looking at the market. The first and most common group is stony meteorites. These make up roughly 94% of all confirmed meteorite falls, which already tells you something important. They are by far the easiest to find statistically, but also the hardest to recognize, precisely because they look the most like ordinary rocks. Within this group, there are two major subgroups, chondrites and achondrites. Chondrites are the most primitive. They haven't changed much since the solar system formed, and they're identified by those tiny round structures we mentioned earlier, the chondrules. The Maryborough meteorite, found by David Hole in Australia, was an H5 ordinary chondrite, meaning it had a high iron content and had been partially reheated inside its parent asteroid, but still preserved a recognizable primitive structure. Common chondrites in good condition typically sell for somewhere between $2 and $20 per gram on the collector market, which sounds modest until you realize that even a modest specimen of a few hundred grams can represent real money. And rarer subtypes, like carbonaceous chondrites, which may contain organic compounds and water-bearing minerals, can command significantly more. Achondrites are stony meteorites that have gone through a melting process inside their parent body, which erases the chondrules and produces a more crystalline, differentiated rock. The most extraordinary achondrites are the ones that came from bodies we actually know, the Moon and Mars. Lunar meteorites and Martian meteorites are so rare and so scientifically important that prices routinely exceed $1,000 per gram, with exceptional pieces going well beyond that. Owning a fragment of Mars is not a figure of speech. These rocks exist. They've been found in deserts and Antarctica, and they are traded in the collector market as legitimate scientific specimens. The second main group is iron meteorites. These originated deep in the cores of ancient asteroids that melted and separated into layers, much like Earth did, with heavy metals sinking to the center and lighter silicate rocks floating to the surface. When those asteroids were later shattered by collisions, the iron cores broke apart, and some of those fragments eventually fell to Earth. Iron meteorites are dense, metallic, and magnetic. They're much easier to recognize than stony meteorites, which is one reason they show up frequently in old collections and on farms. People noticed them because they felt and looked unmistakably different from the rocks around them. The most famous iron meteorites display something remarkable when you cut them open and etch the surface with a mild acid, a geometric crystal pattern called the Widman-Stoughton pattern, formed by the slow cooling of iron-nickel crystals over millions of years inside an asteroid core. This structure physically cannot be reproduced in a laboratory. It takes the conditions of deep space and millions of years to form. When you look at it, you're seeing something that no factory, no forge, no geological process on Earth could ever create. Common iron meteorites sell for roughly $1 to $10 per gram, though exceptional specimens with strong visual appeal or historical significance can reach much higher. The third group, and by far the rarest, is stony iron meteorites. They represent less than 2% of all known meteorite falls. Within this group, one type stands above everything else in terms of beauty and collector demand: the palisite. Palisites formed at the boundary between the iron core and the silicate mantle of large, differentiated asteroids, a place where molten iron mixed with crystals of olivine. the same mineral that on Earth we know as the gemstone peridot.
When a palisite is sliced thin and held up to the light, the olivine crystals glow in shades of green, amber, and gold, suspended in a silver-gray metallic matrix. The effect looks like a stained glass window made from space. It looks like nothing else that exists. Out of the roughly 75,000 officially classified meteorites in the world, fewer than 200 are pallasites. That scarcity, combined with their visual impact, pushes prices to extraordinary levels. High-quality polished slices of the most sought-after pallasites have sold for anywhere from $40 to over $100 per gram. And certain famous specimens, like the Fukang pallasite found in China, have had individual fragments valued at close to $1,000 per gram, with auction estimates reaching into the millions for the largest pieces. Understanding these three categories doesn't just give you a sense of what something might be worth, it also tells you where to focus your attention in the field. A dense, magnetic rock in an area with no obvious geological source of iron is worth investigating. A stony rock with an unusual surface texture and an unexpected weight deserves a closer look. And if you ever find something that looks like metal embedded in a rocky matrix with translucent crystals, don't put it back on the ground. Understanding these three categories doesn't just give you a sense of what something might be worth, it also tells you where to focus your attention in the field. A dense, magnetic rock in an area with no obvious geological source of iron is worth investigating. A stony rock with an unusual surface texture and an unexpected weight deserves a closer look. And if you ever find something that looks like metal embedded in a rocky matrix with translucent crystals, don't put it back on the ground.
Now here's where most people get stuck, and where most meteorite hunts come to a frustrating end. The minerals and rock types that fool people into thinking they found a space rock are so common, so widespread, and so convincing that geologists have a term for them. They call them meteor wrongs. The professor at Central Michigan University who identified the Edmore Doorstop meteorite said she had been asked to examine rocks for 18 years before that one came along. In nearly 2 decades, every single submission had been a meteor wrong. That's not a failure, that's just the reality of how rare genuine meteorites are and how effectively certain Earth rocks can impersonate them.
The most common culprits are worth knowing by name because recognizing them saves you time and prevents false excitement. The first is magnetite, a dark, heavy iron oxide mineral that is naturally magnetic and found in many rock types across the United States and elsewhere. It has a metallic appearance, it responds to a magnet, and it's often dense enough to surprise someone who picks it up for the first time. All of those qualities can initially suggest a meteorite. But magnetite typically shows a dark reddish-brown streak when scraped against unglazed porcelain, a simple test called the streak test, and lacks the internal structure that meteorites display when cut open. True meteorites almost never leave a colored streak. They usually leave a gray metallic one or none at all.
The second major imitator is hematite, particularly a variety called kidney ore or botryoidal hematite, which forms rounded, globular masses that can look oddly shaped and very heavy. Hematite is also magnetic in some of its forms, and its surface can have a dark, almost burnt appearance that triggers meteorite associations. But again, the streak test distinguishes it clearly. Hematite leaves a red to reddish-brown streak, which no iron meteorite does.
Slag is another trap. Industrial slag is the byproduct of smelting operations, the waste material that floats to the top of molten metal and is poured off and discarded. Slag is common near old foundries, railroad lines, and industrial sites, and it can look disturbingly similar to iron meteorites. It's often dense, dark, glassy, and pitted with surface holes. The key differences are that slag usually contains air bubbles and flow marks that reflect its molten origin, often has a glassy texture inside when broken, and is not composed of iron-nickel alloys in the proportions that characterize meteorites. A simple chemical test or X-ray fluorescence can separate them immediately, but even in the field, looking carefully at the internal texture when a fresh break is available usually tells the story. Pyrite, sometimes called fool's gold, is less likely to be confused with a meteorite directly, but it appears frequently in the same conversations because of its metallic look and its tendency to form in heavy, dense masses.
Pyrite has a very different density than iron meteorites, and it weathers into a powdery yellow-orange surface when exposed to the elements, something that never happens to the iron-nickel alloys in a space rock. Dense volcanic rocks, particularly basalt and gabbro, can have the right color and surface texture to fool a beginner. Their weight can be surprising if you're not familiar with the density of common dark igneous rocks. But volcanic rocks are composed of silicate minerals without significant iron-nickel metal, and they won't respond to a magnet the way iron or stony iron meteorites do. So understanding these imposters is just as important as knowing what you're looking for, because the ability to rule out common Earth rocks quickly is what separates a productive search from an endless loop of false leads. You don't need a laboratory to take a first serious look at a suspected meteorite. There are several physical tests that give you meaningful information using tools you either already have or can find easily, and doing them in the right order can save you both time and the cost of shipping a rock across the country for professional analysis. The first test, and the one most people already know about, is the magnet test. Most meteorites contain iron-nickel metal, which means they respond to a magnet. A standard refrigerator magnet is too weak to be reliable. What you want is a strong, rare earth magnet, the kind used in neodymium magnets, which are inexpensive and available online or at hardware stores. When you bring a strong magnet near a genuine iron or stony iron meteorite, you'll feel a clear, unmistakable pull. Even most stony meteorites contain enough dispersed metal to produce at least a slight response. A rock that shows absolutely no magnetic attraction at all is very unlikely to be a meteorite, though there are rare exceptions in certain achondrites. The important caveat here is that a magnetic response alone proves nothing. As we just discussed, magnetite, hematite, and slag are also magnetic. The magnet test filters out most meteor wrongs, but it doesn't confirm anything on its own. The second test is the streak test. Find a piece of unglazed porcelain. The back of a ceramic tile works perfectly. Drag the edge of your suspected meteorite across it. Iron meteorites typically leave a gray metallic streak, or no streak at all. Magnetite leaves a black streak. Hematite leaves a red to reddish-brown one. Slag usually leaves a dark brownish or greenish streak. If what you're looking at leaves a colored streak, you can rule out the most common meteorite types immediately. The third test is density. Meteorites are almost always notably denser than Earth rocks of a similar size. There's an informal phrase used by meteorite hunters, heavy for size, and it captures something real. When you pick up a genuine iron or stony iron meteorite, the weight is surprising in a way that's hard to describe until you've experienced it. You can quantify this by measuring density. Weigh the rock on a kitchen scale, then submerge it in a measured container of water and calculate the volume by displacement. Density is simply mass divided by volume. Iron meteorites typically have densities between 7 and 8 grams per cubic centimeter. For comparison, common granite runs around 2.7 and basalt around 3.0. Even ordinary chondrites, which are less metallic, generally land between 3.0 and 3.7, noticeably denser than most Earth rocks of the same size. The fourth test involves looking at the surface carefully. Freshly fallen meteorites often have a fusion crust, a thin, dark, glassy coating that formed when the outer layer melted during atmospheric entry. This crust is sometimes described as looking like a thin layer of burnt paint, or like the skin of a dark fruit. It's rarely perfectly preserved because weathering degrades it over time, but remnants of it can often still be seen on fresher finds. If you see a rock with a smooth, dark outer layer that doesn't quite match the interior material you can see where it's been chipped or broken, that's worth noting. On iron meteorites that have been weathered, look for regmaglyphs, the thumbprint-like indentations on the surface that form aerodynamically as the outer material ablates during atmospheric flight. This is one of the features that initially caught the attention of the Melbourne Museum geologists when David Hole brought them his rock from Australia. Regmaglyphs are not impossible to find on Earth rocks, but they're unusual, and combined with other indicators, they carry real weight. The fifth, and perhaps most telling field observation, is context. Where did you find it? A rock sitting on top of undisturbed soil in an area with different underlying geology, with no obvious local source for its composition, is more interesting than the same rock found in a riverbed surrounded by similar-looking material. Meteorites land randomly, which means they don't belong to the local geological story. They stick out, not always visually, but contextually. A heavy, dark, magnetic rock sitting on a surface of sandstone or limestone is more suspicious than the same rock in a mineralized basalt field. Paying attention to context is a skill that develops quickly with practice. If after all these tests you still believe you might have something real, the next step is professional analysis. You'll want to contact the geology department of a local university, a natural history museum, or a certified meteorite appraiser. Never cut or grind the specimen before having it evaluated. You risk destroying the fusion crust, the internal structure, and potentially the provenance documentation that adds significant value to the piece. Ship it carefully, fully insured, and document it with photographs from multiple angles before it leaves your hands. The most common meteorites, ordinary chondrites, which make up the majority of all known falls, are genuinely not worth a fortune. They're scientifically valuable to researchers, but the collector market is relatively well supplied with them, and prices for unclassified material in average condition can be quite modest. A common chondrite without documentation might sell for $2 to $5 per gram in the current market. That sounds reasonable until you consider that most people who find an unclassified meteorite have no way of knowing what subtype it is, or whether it has any characteristics that distinguish it from the thousands of other similar specimens already cataloged. What makes a meteorite valuable isn't simply being a meteorite. It's a combination of factors that you need to understand clearly before you decide what to do with any find. The first factor is type and rarity. As we covered in the earlier section, lunar and Martian meteorites sit at the top of the pricing scale, often exceeding $1,000 per gram. Pallasites and other rare stony irons command strong premiums for their visual appeal and scarcity. Carbonaceous chondrites, which may contain amino acids, water, and complex organic chemistry, are prized by researchers and can attract institutional buyers willing to pay well above the common chondrite baseline. Iron meteorites from famous witnessed falls, like the Sikhotia-Lin event in Russia or the Canyon Diablo crater in Arizona, carry collector interest that pushes prices higher than anonymous specimens of the same type. The second factor is condition. A meteorite with a preserved fusion crust, minimal weathering, and no damage from improper handling is worth significantly more than one that's been exposed to the elements for decades or that someone tried to cut open with a grinder before knowing what they had. The Edmore Doorstop meteorite in Michigan maintained good condition despite its long stay on the farm, partly because the farm environment protected it from the worst weathering. The Maryborough meteorite in Australia, on the other hand, had its surface exposed to acid by its owner before anyone knew what it was, a mistake that reduced scientific data available from the outer layers. Condition is something you can protect from the moment of discovery by handling the specimen carefully and keeping it dry. The third factor is documentation and provenance. A meteorite with a clear, documented discovery story, ideally with photos of the find location, GPS coordinates, and confirmation of the geological context, is more valuable than the same rock without that information. The fourth factor is classification. An officially classified meteorite, one that has been submitted to the Meteoritical Bulletin database and assigned a formal name and classification number, is worth more than an unclassified specimen, even if the underlying rock is identical. Classification requires professional laboratory analysis and peer review, and it confers a level of scientific legitimacy that the collector market rewards. If you have something that passes all the initial field tests and a professional confirms it looks like a meteorite, pursuing official classification is almost always worth the time and cost. Putting this all together, here's a realistic picture of what the market looks like for common finds. A small, average condition, ordinary chondrite without classification might bring a few $100s from a private buyer. The same rock, officially classified, in good condition, with documented provenance, might bring several times that from a serious collector or a regional museum. A unique type or a specimen with exceptional preservation or story could command significantly more. And something at the rare end of the spectrum, a palisite, a lunar fragment, a Martian achondrite, belongs in a completely different conversation, one that involves auction houses, institutional buyers, and prices that can reach into the tens of thousands of dollars, even for modest-sized pieces.
The key takeaway is this: don't sell anything fast and don't sell anything cheap before knowing what you have. The people who lost money on meteorites almost always made the same mistake. They moved quickly, without knowledge, and handed something to the first buyer who expressed interest. They had no reference point for what a fair price looked like, no understanding of what type of meteorite they were holding, and no documentation to back up their claim. The people who came out well were the ones who took their time, got a proper identification, and understood the market well enough to recognize a fair offer when it came. Now, let's say you went through everything in this video. You found an unusual rock, ran the magnet test, checked the density, looked for the fusion crust, and you're convinced something is worth investigating. But the lab comes back and tells you it's not a meteorite. That doesn't mean you came away empty-handed, because the same curiosity and the same ability to read rocks, minerals, and geological signs that drives a meteorite hunt is exactly what leads people to find gemstones, tourmalines and pegmatites, garnets and schist outcrops, sapphires and alluvial gravel, even rough diamonds and kimberlite-bearing soils. The skills overlap more than most people realize. Learning to notice what's unusual, heavy, or out of place in a natural environment is the foundation of all mineral prospecting, whether you're chasing something that fell from space or something that formed deep in the earth.
And if that world of gemstone identification and field prospecting interests you, if you want to know what to do when you find a crystal you can't identify, how to test it at home without expensive equipment, and how to avoid selling something valuable for a fraction of its real worth, that's exactly what the Gemology Journey for Beginners training covers. It was built for people who are just starting out and want practical, accessible knowledge that actually applies to real finds in real conditions, without needing a geology degree to follow along. You can find the link in the description. And if now isn't the right moment for that, you can still keep learning for free right here by subscribing and watching the next video that's already appearing on your screen. Thanks for liking and subscribing. Good luck, Gem Hunter!